Hello, thank you very
Go
much.
ahead. I think I started recording. Yeah.
Okay, yeah. Thank you. So yeah, so the talk is about Baryon asymmetry of the universe, and in these dark times, I think I will mention Sakharov's name many times, but in this dark times, I want to just to mention that in 1975 he got a Nobel Peace Prize. You see the formulation here. He was one of the creators of the nuclear bomb in USSR. Then he did more peaceful things like tokamak. Then he played a really important role for like nuclear ban, partial nuclear ban. And in 1967, he created a paper, very important one, on fundamental physics, on cosmology, about the asymmetry, the Baryon asymmetry of the universe. And actually, he was in internal exile in Soviet Union because his fight for the rights and freedom and cooperation between all nations. And now, unfortunately, we are back in very dark times. Today, the Russian parliament agreed on the law, which assumes like 15 years of imprisonment for what they call fake news about military operation, basically everything which disagrees with government. So people are really scared, but I really hope that scientific collaboration can bring some understanding in these dark times. Anyway, let's proceed with the subject of the talk. And here's my outline. I will just first mention Baryon asymmetry and Sakharov's conditions, then the seesaw mechanism for neutrino mass generation and leptogenesis, and then I discussed the recent results which we have obtained with Misha Shaposhnikov and others, and then some phenomenological implications of that. By the way, Andrei, how much time do I have?
It's 1 hour in general. Yeah.
Okay, perfect. So yeah, here is the list of the references. We worked a lot with Misha Shaposhnikov, Shintaro Ujima, Yurai Klaric on the leptogenesis part, and with Jean Lu and others. Jean-Loup Tastet was a master student at TPFL. Now he's already a postdoc at Madrid. We work on the phenomenological side of right-handed neutrino or heavy neutral leptons. Okay, so the Baryon asymmetry of the universe. We know that there's no antimatter present in the universe. It's known from different sources, but the most accurate ones are actually the observation of CMB and the observation of the primordial elements in intergalactic medium, and they tend to agree very well with each other and give the number of baryons over the photons in this range. So this number is one of the ingredients of the cosmology, and we know for sure that the Baryon asymmetry was there. There was a tiny asymmetry between baryons and antibaryons. Then on all antibaryons have annihilated, and we left with this number. Okay, so it's a tiny number, yet it is not so easy to come up with. And in 1967, Sakharov proposed three conditions which should be satisfied in order to obtain the Baryon asymmetry of the universe. So first of all, the Baryon number must be violated because it is the symmetry of the standard model, the global at tree level, but to generate asymmetry, it should be violated. Then C and CP should be violated to protect it from washout, and deviation from terminal equilibrium is needed. So in the standard model, the first condition is satisfied because there are non-perturbative processes mediated by sphalerons at high temperatures. At temperatures larger than 130 GeV, the Baryon number is violated. These two conditions are not satisfied because the CP asymmetry in the standard model is the way too small if one calculates this accurately, and the deviation from terminal equilibrium due to expansion of the universe is also not enough. Okay, So let's look at this standard picture, but I added some more things here. So this is the evidence of the baryon asymmetry of the universe coming from the cosmic microwave background. Another piece of evidence comes from the epoch of nucleosynthesis, but the generation of this asymmetry should occur earlier. So in fact, since in the standard model, B violation is absent, basically absent at low temperatures, low meaning below electroweak temperature. So the baryon asymmetry cannot be generated here. So we need to speak about this region. So it's really very early universe. And if we will have some evidence of some particles responsible for that, that would be an evidence of the earliest processes in the universe, a direct evidence. Okay, so in this plot, we're interested in this region. But okay, the baryon asymmetry is not the only problem which the standard model of particle physics cannot address. Another one is neutrino masses. So we know very well that neutrinos do oscillate. Here is just a plot from the global feed of all experimental data. And we are pretty sure that neutrinos do oscillate. And for that, they need to have mass splittings. And they must be massless. But in the standard model, massive, but in the standard model, they are massless. So how can we solve this puzzle? First of all, the mechanism has been, we will discuss the seesaw mechanism. We introduce 2 or 3, or at least 2 right-handed neutrinos to the standard model. So we have the Lagrangian of the standard model, then these new particles. Throughout this talk, I will call them heavy neutral leptons because this is how the experimentalists call them. And these new particles, they can, unlike all other standard model particles, they can have a Majorana mass term here. And then one can obtain parametrically small neutrino masses. And important consequence of the mechanism is that neutrinos, the flavor eigenstates, now contain both light mass eigenstates.
Sorry to interrupt, Ina. Calum Anderson, could you please mute your mic because we can hear background noise, please? Thanks.
Oh, yeah, sorry about that.
Sorry, Ina.
Yeah,
sorry to interrupt. Sorry.
So we have this slide here. I will return to the quantities to theta and u square quite often throughout the talk. So the active neutrinos, the ones which we know, the flavor states mix with heavy states, which I will call heavy neutral leptons, with these small mixing angles. The mixing angles are basically proportional to Yukawas and inversely proportional to the masses of these heavy neutral leptons. I will also introduce a quantity when I sum over all mixing angles just to characterize the mixing between heavy and light states in some short way. This is u squared. Okay, this is maybe the most minimal solution to the neutrino masses. However, apart from solving the neutrino mass puzzle, it can actually help us with the baryon asymmetry. This is the slide about what Misha Shaposhnikov calls neutrino minimal standard model, MUMSM. So from this nasty plot, we go to the very symmetric and nice one with 3 right-handed neutrinos. The lightest of them is a dark matter candidate. It should be very, very light. And the 2 others, we will consider only 2 right-handed neutrinos, which mix with active neutrinos. They are responsible for the baryon asymmetry of the universe and for the masses of light neutrinos. And how this work, this is basically the subject of the talk. And what are the masses?
Sorry, Ina, can I ask a question here?
Sure.
So you're taking the right-handed neutrinos to be really small now, right? Mass.
So small compared to GATT scale, say.
Yeah.
So it could be GeV scale. Yeah.
The original motivation was to have very heavy right-handed neutrinos. That's how the seesaw mechanism works, right? To have part of the neutrino mass hierarchy coming from a big mass scale. But now you lose that motivation here when you make the right-handed neutrinos really small, if you don't have an explanation for that.
So in some sense, yes, but like the GATT, we obtain the GATT scale if we take Yukawas of order of 1.
Yeah.
Here, our Yukawas, I mean, but electrons Yukawa is not of order 1.
Right.
If we take, I cannot tell you exact numbers. If what's the mass if we take electrons Yukawa for this right-handed guys? I think it should be some PV maybe scale, something like that. But yeah,
But
in this sense, yes, I mean, it is still the neutrino masses are still parametrically small because there will be like Yukawa square divided by the mass of this heavy guy. So
well, the Dirac, I mean, I guess you're saying that the Dirac mass is still much below the
yes,
the
exactly.
right-handed neutrino mass. So you still have a little seesaw going on, right?
Yeah, exactly. The Dirac mass is very small, but this is in the cost of having a small number.
Yeah.
The small number being the Yukawa.
Okay, thanks. Yeah.
Yeah.
Well, I guess, Tony, you should view this model in this context of this extreme point of view of like absolute desert all the way to the Planck scale.
Yeah,
that Michael
exactly.
was pushing for a while, right?
Exactly. No, because you're right. I mean, you want to try and look for new physics. So you want to push to this extreme and see if you can have signals of a light right-handed, of sterile neutrino, right? Yeah. No, it's all good.
It's surprising that it may work with such a low scale.
Yeah. I see. Yeah.
But yeah, actually, in several slides, I will show that it works till very high scales with like in unified description. So anyway, let's see. This is some references. So the idea how very light heavy, let me call them HNLs for sure. So the idea how very light HNLs can generate the symmetry, it was proposed by Akhmedov, Rubakov, and Smirnov. In the case, it was working with 3 HNLs. Then Asaka and Shaposhnikov improved the description. They found out that just 2 HNLs were enough. And then there was a lot of people working on this model. So pretty sure I missed somebody here. But what I was showing so far is pretty well-known stuff. So this is my own slide from 2 years ago. And the idea was, okay, this is leptogenesis. So meaning we generate lepton asymmetry. It is converted to the baryon asymmetry by the Fellering processes. And there are different mechanisms. It was well known. First, Fukugita and Yanagida suggested the thermal leptogenesis, which works somewhere in the GATT scale. Then Akhmedov, Rubakov, Smirnov.
Actually, let me just, they did not propose thermal leptogenesis. What they proposed actually was non-thermal leptogenesis. Their right-handed neutrinos never needed to be in equilibrium. They just needed to be produced early on. Whatever mechanism they produced, it was enough, because once you have them, if their lifetime is such that they're out of equilibrium when they decay, that gets you the lepton asymmetry. They never actually used the fact that you had to generate them thermally. They just assumed that they were present. You calculate their lifetime. It's just like it was really a copy of the initial out of equilibrium decay scenario from GUTS. Instead of using either heavy Higgses or heavy gauge bosons, they used this heavy right-handed neutrino, but they didn't need to assume that it was produced thermally.
I see.
It works fine. You just this idea that you had to create the right-handed neutrinos from the thermal bath is not true.
But I think with very large Yukawas, they would be created anyway. I mean.
Well, no, it depends on things like the reheating temperature.
Yes,
so all these people
exactly.
trying to, but you don't need that, right? You don't need any of that.
Yeah, that's true. That's true. So if you assume the preheating temperature large enough, then yeah, there will be.
No. You don't need.
But you don't need that. I see the point. Yeah.
Right. I mean, the simplest, if the inflaton, for example, has a decay channel and right-handed neutrino is in the decay chain, you'll produce the right-handed neutrinos and they'll already be out of equilibrium. Right. And then when they decay, they produce the lepton asymmetry that way.
Yes. But then I think still most of the works, like after that, they considered like thermal initial
Yeah,
condition.
many people then afterwards, that's true, but
Yes,
it,
yes.
but you don't need any of it, right? I mean,
Absolutely, yes, this I agree absolutely.
Yeah.
And again, we will have the plots which show this as well.
okay.
Okay,
Just a-
yeah. Then also it has been understood, but it was understood earlier, but then Apostolos Pilaktis realized that this the resonant enhancement, if you have very degenerated mass HNLs, can lower the mass scale significantly, but still it was people consider like three different mechanisms. There were three communities, and the point of this talk is that this picture should be reconsidered, and that's what I will be showing here. Okay, so why we thought that there's a gap? So one idea, the gap from very low scale, low masses comes about because of the following. So if the HNL becomes as heavy as W, there are new decay channels which open, and then the deviation from the equilibrium, because this mechanism is freezing, they do not reach thermal equilibrium while generating asymmetry. But if this new decay channel opens, and the inverse decays as well, they reach equilibrium very quickly, and the Sakharov's condition is not fulfilled. And then somewhere around the mass of the W, this mechanism should stop. Another point is that if in resonant leptogenesis, people usually assume the thermal initial conditions. With thermal initial conditions, if these heavy neutral leptons are like lighter than the Sphaleron temperature, they decay before, and there's no time to generate the asymmetry before the Sphaleron transition. But so basically, the question is there a gap? Until 2020, it was assumed that there is a gap, and also the experimentalists thought so. But we need to update the things. So the description: if you have two right-handed neutrinos which can be degenerate, the system is described by the following kinetic equations. So in principle, those are integral differential equations. This is the lepton numbers. So we write down the combination which is not affected by sphalerons. And then we also account for the spectator processes for this susceptibility matrices. So this is the part describing the washout of the lepton number and generation of the lepton number by this HNLs. And this is the part describing two heavy neutral leptons. The oscillations, this is the expansion of the universe, the oscillation term, the rate of the interactions, and then finally the thing, like how the asymmetry is transferred to the leptonic sector. Okay, there are some simplifications. One can assume that the momentum dependence of this matrix, so this is 2 by 2 matrix of densities, which depends on momentum mode as well. One can assume that the momentum dependence is equilibrium one, and so on and so forth, and solve them. One still ends up with 11 stiff differential equations, which should be solved numerically. And then there was a lot of development since 2014. First, the role of processes with helicity flip, like you have this HNL, it can decay with helicity flip or without, and the processes without helicity flip, they suppressed by the mass, and we thought, okay, there's an m over t squared suppression, these processes could be neglected. No, they cannot, because they are multiplied by some other Yukawa combination. Then the rates itself, they should be computed, these rates in the kinetic equations. There are many very delicate processes like there are soft scatterings. If this HNL decays to some products which fly in forward direction, there is exchange of gauge bosons in between. and the one has to do so-called Landau-Pomerantchuk-Migdal resummation to account for that, and this is really complicated stuff. And Mikko Laine is the main expert on that. He and Jacopo Lieri, they did a lot of work in this direction. Then the spectator processes should be accounted for, and so on and so forth. But the main improvements are these two. Now, these two plus the rates for heavy HNLs, they have not been computed for the HNLs with this in this mass range. They have not been computed. We did this as well. So what we get, there is no gap. Basically, leptogenesis, the oscillations can work till very high scales. And the resonant leptogenesis with thermal initial conditions, it also works for right-hand neutrinos as light as 5 GeV. And the reason why leptogenesis, why the window does not close around the W mass, as I was saying, is the following. This of course depends on the parameters, but for some parameters, the washout of the asymmetry is very hierarchical, so the total asymmetry survives. And the reason why the window doesn't close here is that even though the deviation from equilibrium is very tiny, the asymmetry which can be generated, I mean, we need 10 to minus 10 asymmetry, and even this small asymmetry can be generated with tiny deviation from equilibrium. But this we found out only numerically. It was not really possible to estimate analytically. Just to clarify what we have, so it's more appropriate maybe than to call them two mechanisms, two regimes as leptogenesis via oscillations, as we initially called them, resonant leptogenesis. This is rather freeze-in and freeze-out generation. So let me try to guide you through this plot. So this is time. This is the number density of the HNLs divided by the photon number density, and this is the equilibrium value. So here they start to decay. And the blue line is the actual value. So you see there are two moments when the deviation from equilibrium can happen. First, during freeze-in, when they have not been created yet from the thermal plasma, and there's a huge deviation from the equilibrium. But then if they decay with some time lag, there's also another deviation from equilibrium during the freeze out because of the small UCAVs. So the difference between two leptogenesis mechanisms is in fact just where the asymmetry, the generated asymmetry, is translated to the baryon one. So if the spiral freeze out happens here in time, then it's the asymmetry generated during freeze-in got frozen because the sphalerons no longer convert this to the baryon asymmetry, and that's it. So this is the freeze-in generation. On the other hand, if the sphalerons freeze here, you have the freeze-in, the asymmetry generated during freeze-in, then it washed out during the equilibrium, then a new asymmetry is generated during freeze-out, and finally it stops to be converted to the baryon asymmetry. Okay, so this is the difference between two mechanisms, well, two regimes of the same low-scale mechanism. And now, actually, to this question of how heavy or how light they can be, one can study the equations and see that the solution at high enough masses just scales in this way. So we scale mass, the mass splitting scales like that, and that's it. So the baryon asymmetry can be generated within this region and within this region as well. Our kinetic equations should be modified a bit at 10 to 6 GeV. So we didn't solve them here because so some modifications should be done, but they are very trivial. Around 10 to 9 GeV, the modifications are more complicated, but it's already where thermal, whatever, high scale leptogenesis works. So basically, the same description is valid over many orders of magnitude till GATT scale. So this lower line here, it's so-called seesaw line, because if you just take the UCAVs in such a way that you generate neutrino masses, the mixing of heavy neutral leptons with neutrinos cannot be smaller than this value here. At the same time, it cannot be larger than this value, otherwise the washout wins. And what we show here in color is the mass splitting, delta M over M. So you can see the mass splitting can be as large as 10%, for example. Here it is less than 1 per million, 1 part per million. But this is the result. So there is no gap, and basically this heavy neutral leptons can be everywhere. We can search for them only here. So this is 3 example lines. This is FCC, high Lumia LHC, and SHIP. The rest of the parameter space is intact. So we need to figure out maybe some alternative ways, if they exist, how to understand if something is here. But that's what we have about the searches. And just let me briefly show you the slide. So what I was talking about, the mechanism with 2 right-handed neutrinos. But you can have three of them, right? This has been studied by these guys, and the parameter space is much larger. So basically, everything is allowed here. The experiment, I mean, it's weaker than the experimental bounds in some range. Okay, so that was the cosmological part. Let me maybe now switch to the experimental searches. So this is the plot from Physics Beyond Collider report, and you see the main aim of showing this is just to show it is very busy. There is a lot of experiments looking for heavy neutral leptons, and yeah, of course, very long range of masses. And one of these experiments is SHIP. SHIP stands for Search for Hidden Physics. And this is a beam dump experiment at CERN, which uses the 400, it's a planned experiment, and this plan that it will use the 400 GeV proton beam from SPS, and there's a huge empty volume where the HNL is produced in the target. The proton beam hits the target. The HNL is produced in the target. It decays in this volume, and there's a calorimeter tracker and so on. The SHIP was not supported by European strategy, so it was said that this is the flagship experiment, but we don't have money for that. Still, CERN supports R&D for SHIP, and the BDF, basically the facility where the experiment will be located, is now a separate. There is a separate group which is supported by CERN. So BDF is now a separate entity from SHIP. But unfortunately, all these slides are from pre-war time, because now next Monday there will be a CERN council discussing the situation with Russia. A lot of members of the collaboration are from Russian institutes, and how the interaction will go, it's not clear absolutely. Okay, but still, SHIP is a flagship experiment for this type of searches. And one funny thing is that it cannot even check the nature of heavy neutral leptons. Suppose we found these particles, but we don't know, are they Majorana or Dirac? Just some fermions decaying to pions and leptons. And normally in colliders, you can easily distinguish Majorana and Dirac HNLs, because Majorana particles allow you for lepton number violation. And the signature which they like very much in colliders is same sign dileptons, because here there's a displaced vertex and the background is very low, because you have L+, L+. The same process can take place at chips where H is some heavy meson, like B meson decaying to something, creating an HNL which decays. The problem is in the beam dump experiment, this HNL will be absorbed in the target. So the information about its charge is completely lost. So how you can distinguish these two types like Majorana and Dirac, because you don't know the sign of this lepton. In fact, one still can distinguish them. So how it works? The HNL, which is produced here, it actually it is produced from a scalar from meson, which is scalar. And if you produce it along with, say, L plus, the helicity is conserved, and the charge of this meson, of this lepton, is kind of, you can infer the charge of this lepton from the spin, from the helicity of the heavy neutral lepton. This is in the rest frame of decaying meson, but then there are complications because they are all boosted. But still, looking at the angular distribution of decay products of the HNL, you can infer the charge of this initial particle. So you have something like that: LNV and LNC in the rest frame of the HNL. They decay like that for L plus and L minus, and in the lab frame, you will have something like that. Still, it's not all the complications because you are not limited by two-body processes. There are many different processes, many different channels with different decay, with different final states, and so on. So one has to go for Monte Carlo simulation. We have written a code which uses the correct matrix elements with angular correlations. The only downside of this code is written in Julia language, so nobody can use it. But this is one result. It's a correlation between the energy of the HNL and the PT of the lepton, which you see in the experiment. This you see in the experiment, and this you can reconstruct. Okay, you can see some difference by eye. One can use machine learning to train the classification. We used so-called boosted decision trees. So the classification is not perfect. It's at most 65%, but this is actually enough. So if we, this is the same plot, U squared in this, U squared versus the mass. This is the sensitivity of ship. And this line shows the region where we can distinguish Majorana and Dirac fermions. So above this line, we can distinguish, we can determine the nature of the fermion, of the HNL. And you can see, you see this is better than the closest competitor. So ship will be better than, at the time it was an A62 in the beam dump mode. Now it could be shadows or whatever, but still. So this line is below the competitors. This is for mixing with electron, and this is for mixing with muon. Okay, but if we would be extremely lucky, the following can happen: the resolvable oscillations of HNLs. So in the new MSM, one wants to generate not only the baryon symmetry of the universe, but also the dark matter. This is tricky because dark matter, to produce dark matter, sterile neutrino, you need the Dodelson-Woodrow, the usual thermal production is ruled out by astrophysics data, by gamma rays. And then you need some lepton asymmetry to enhance the production of dark matter. This lepton asymmetry can be produced if the mass splitting between two HNLs is really, really tiny, around 10 to minus 7 eV. So within these regions, the right amount of dark matter can be produced. This is the old paper, should be updated. We work on that, but just to take some value from here, we do the analysis and we see that precisely with this 10 to minus 7, we can see the oscillations of HNLs at ship. But yeah, this would be, of course, amazing. Okay, next thing. What about the current analysis? So there were, like I showed you in this plot, there is a lot of experiments already. Some regions are excluded. Could it be that they are not really excluded? So let's consider again the model with two HNLs. In this case, the neutrino data, the mixings and the mass splittings can be, if we want the CISO to give us the correct neutrino observables, not all possible. So not all values of mixings are allowed, but they are just restricted by the neutrino data. So in this triangle, what we have is the mixings of HNLs with neutrino divided by the total one. So they sum up to 1. That's why I use this ternary plot. So this is the allowed values of the mixing angles. You see, if neutrino active neutrino masses follow the normal hierarchy, we're in this blue region. If the hierarchy is inverted, then we are somewhere in the green region. Okay, but the experiments usually report the sensitivity for single flavor mixing, like UE equal only UE is not equal to 0, or only U mu is not equal to 0. Does this picture change something? In fact, the answer is yes. As an example, we took the Atlas trilepton search, this diagram, have 3 leptons in the final state, and they reported the results for mixing with electron or mixing with mu. Now, Jean-Loup reproduced all analysis. He done really thorough work reproducing all Monte Carlo and so on in MatGraph, and by reproducing the single mixing analysis, now we can have the now once we have control over that, we can consider different values of these mixing angles within these colored regions. So you can see that this is the original results of Atlas, and these lines correspond to benchmarks here. So these lines can be basically in a huge range. So it could happen that for specific mixing pattern, which is allowed by neutrino oscillation, the HNL is actually here. So even though it is reported as excluded, it is not the case, because if you have, for example, UE and U mu, the lifetime is not like what it was assumed for UE single mixing, and it changes the results. And the same for the inverted hierarchy. So basically, these guys, they can hide somewhere here. And the exclusion limits are much weaker than they have been thought of. In the case of free HNLs, this will be even more drastic, because it's more freedom is allowed. So maybe last thing is that they can even be very, very light. We did the following analysis. We took all the experimental data and tried to recast it in such a way that we again used only the mixings which are allowed by the neutrino oscillation data, and found out that around the pion mass there is a tiny window which is allowed by leptogenesis, experimental constraints, and BBN. By BBN here I mean the following. So there's nucleosynthesis, and if the HNL decays during the nucleosynthesis, it spoils down the eventual abundance of the light elements. Okay, so there is a tiny window. So it could happen that the HNLs are very light, quite strongly coupled, but still have not been observed. why it is close to the pion mass is because the experiments which look for HNLs in pion decays, they don't have sensitivity here, and those which look in the kaon decays, there's they lose sensitivity in this region because of some background from photons. Okay, in the near future, this region can, well, 10 years or something like that, this region can be probed by DUNE. And even if not direct experimental probe here, for example, if the delta, the CP violating angle is measured by DUNE, and if it happens to be here outside this red region, then this funny region here can be excluded. Okay, that's basically it. So leptogenesis really provides a relation between neutrino physics and the very early universe. And as we showed, the low scale leptogenesis is actually works throughout the cold mass scale. The same description is valid basically up to cut scale. And then if the HNLs are light enough below 100 GeV, they could be detected at experiments. And if this happens, this will be the discovery of the origin of neutrino masses and the baryon asymmetry of the universe simultaneously. So I think the experiments looking for them are really motivated from this perspective. Also, there are complementary strategies like colliders and beam dump experiments. And finally, a lot of interpretation is needed to understand what is really excluded, because as we have shown in the model with two HNLs, the regions which are excluded by this single flavor mixing assumption are not really excluded, so they can hide somewhere there. Okay, that's it.
Yeah, thanks, speaker. Are there any questions?
So,
So what's the latest on the ship story? Is it going ahead, or is it applying for funding from CERN? Sorry, it's not a scientific.
So, I mean, since last week, I'm about to answer, but since last week, everything has changed because a lot of Russian institutes participate, and now it will not be possible. Before that, the situation was the following. So despite that it was not supported by European strategy, the CERN was included in CERN midterm strategy, and there was money for R&D. And then CERN also wanted to take care of BDF. There's a lot of research, maybe some other position. I mean, initially it was well, like they consider different new places for the facility. It could reduce the cost. Maybe they will reduce the size of the experiment by, let's say, 10% or something like that.
So this you're talking about maybe ship going in place of an A62, right?
This I don't know how much I can disclose about.
You don't have to answer. This is the mind.
Yes,
I see.
But I mean, I really have no idea what will happen on Monday, because.
Okay. Thanks.
So I had a question about just the range of the right-handed neutrino masses. You said that now leptogenesis is valid from 0.1 GeV all the way up to the gut scale.
Yes.
So what happens below? Can you go from how does it look going from 0.1 GeV all the way down to the Dirac limit? I mean, I understand that maybe some region there is already ruled out, but can the mechanism work all the way down to the Dirac limit or not?
To the Dirac limit, I'm not sure. So I think there was one work where they considered like NV masses, but let me show some exclusion limits. The reason why we didn't think much about that is that if they are very light, they become they can spoil this nuclear synthesis.
Uh-huh. Yeah, yeah.
So that's the issue.
Yeah,
But if they even lighter, I think it can work again. I mean, they will still generate the asymmetry, but they also spoil the nuclear synthesis.
Yeah, yeah. I just meant assuming that it's not ruled out experimentally, can the mechanism work all the way down to the Dirac limit? Yeah, I know. I understand that as they get light, then they
Well,
might
Maybe you can just expand the model a little bit, right? Make the two neutrinos to annihilate into two light scalars, right? And the scalars decay or something like that. Then you probably can go below.
Why?
But somewhere the
Okay.
lepton asymmetry has to come, right?
Yeah, but you have the Majorana mass still.
Yeah, no, what I'm saying is you can, the problem is that you have too much stuff locked into the heavy particles at the start of the BBN. So what I'm saying that you can, I haven't done it, but you can probably modify the model by the expense of other mechanisms of diffusing, suppressing them, right? Not through the weak decays as it would, right? If it's a weak decays, then you have a problem on your hand because these guys are too long-lived, right? But if you first sort of semi-annihilate them into something, and then they decay, then it's fine, right?
No, but also speaking about Dirac limit, I'm not sure. The reason is the following. So you see this this line here, the straight part of the line is U squared proportional to m neutrino over m, which means that there is no cancellation between two Yukawas. Otherwise, and for example here, the Yukawas are cancelled in such a way that you still have the small neutrino masses, but the Yukawas are much larger than this value. Than this value. So if HNLs become very light, the Yukawas become really tiny, and the Frezin takes.
But that's okay because you're going to the Dirac limit, right? And the Yukawas are supposed to become tiny, right? Because eventually, once you go to the Dirac limit, then you have to explain everything with a Yukawa coupling. So that's okay.
Yes, but then the processes do not start before the Spalaron freeze out, because the tiny Yukawas means you still have freezing, and the interaction rates are not large enough. So,
yeah,
so
but
you still can go to lower masses, but then you will have the Yukawas which have some conspiracy to cancel each other to give you the neutrino masses. So I think like Dirac limit is not approachable. But I mean, I never thought about that like properly. But I think I would doubt that you can really have Dirac limit. I mean, if we forget about nuclear synthesis.
Yeah, because you were trying to argue whether neutrinos are Dirac or Majorana, but if you could make an argument that in this mass range, right, that as you go to the Dirac limit, that neutrinos shouldn't be Dirac because it can't produce the baryon asymmetry, then that would be a much stronger argument. But I think people have models for producing the baryon. I think there's something called Dirac leptogenesis, actually. So in the limit.
Yes.
And I think it's this freezing mechanism that they rely upon. So
yeah, I think they need some other particles, if I remember correctly. I mean, it's not, but actually no. Actually, the original RAS mechanism with free HNLs, it works for Dirac neutrinos as well.
Yeah,
for sure.
Because
the original
I think
paper they considered both.
Yeah, because if you can argue that the leptogenesis works, I mean, it's more compelling than that the neutrino is Majorana. So I was just trying to weigh up one possibility over the other in terms of the producing the baryon asymmetry. So
no, yeah, I don't have such arguments. That would be
okay. Yeah,
would be cool.
More questions? So why did you choose Julia to write your code? Why not C++? I mean,
No, I mean C++ is still too
Okay.
complicated. It was some. I mean, there is still quite heavy numerics because you want to sample the decays, like some rejection sampling. Then you want thousands and thousands, tens of thousands of particles. So it should be fast. Python was quite slow.
Yeah.
But then C++, I mean, no, I think it takes too much time to develop something in C++.
I mean, you could have like made the interface in Julia, but all really, numerics.
But yes, so for example, Pythia is in C++, and we did a master project at EPFL trying to implement this Angular correlations in Pythia. It was a nightmare. I think it's already in some official Pythia version, like Angular correlations, but not correct matrix elements of the case. And it was complete nightmare to implement this in Pythia. But it's not because of C++, but Pythia is a huge code, and yeah.
All right, then. So if there are no more questions, let's thank the speaker again.
Yeah, thank you very much.
Thank you.
And see you next time.
Hopefully next time we'll meet under happier circumstances. Thank you.
Absolutely, yes. Okay.
Thank you.
let's
Thank you
hope
very
that-
much, Ina. Thank you.
Yeah,
Thanks.
thank you.
Thank you.
Bye-bye.
Bye.
Bye.